Hello students, I hope you all are doing good. So the topic that we are going to discuss today is electromagnetic induction, NCERT section 6.6, example 6.6 and 6.7. So this is the disclaimer. Learning objectives. After this lecture you will be able to understand and calculate the motional electromotive force, that is motional EMF, in conductors moving through magnetic fields, including its application in practical scenarios. So the index of topics that we are going to discuss today is NCERT section 6.6, motional electromotive force, example 6.6 and example 6.7. So motional electromotive force definition. The EMF induced by the motion of a conductor in a constant magnetic field is called motional EMF. Okay, so by the name it is representing motional. Okay, it means due to motion. So the EMF induced by motion of a conductor in a constant magnetic field is called motional EMF. Okay, we are moving a conductor in the constant magnetic field. Okay, how we are moving that conductor, we are going to see it. When a conductor moves in a magnetic field, the Lorentz force acts on the free charges. Okay, so we know that on the moving charges there is a Lorentz force, but inside a conductor, due to electric field, there is no force because electric field doesn't exist inside the conductor. Okay, so only magnetic force will act on the moving charges present in the conductor. Okay, so Lorentz force is here for magnetic force only. Okay, so when a conductor moves in a magnetic field, also there is only magnetic field. Okay, so there is only magnetic force. In Lorentz force, E is 0. So when a conductor moves in a magnetic field, the Lorentz force acts on the free charges within a conductor, causing them to accumulate at the ends. Okay, so moving charges will experience force. Okay, and this force is perpendicular to both the direction of velocity of moving charges and the direction of magnetic field. Okay, so magnetic charges, these charges will experience force perpendicular to their direction of motion. Okay, so they will start, their motion is along the conductor. Okay, so after experiencing force they will start moving towards the ends, and this thing causes them to accumulate at the ends and creating a potential difference. Okay, so understanding the concept of motional EMF, consider a rectangular conductor PQRS placed in a uniform magnetic field B that is perpendicular to the plane of the conductor as shown in the figure 6.10. Okay, so here is the diagrammatic representation. So you can see there is a magnetic field. It is represented by cross sign. It means that magnetic field is perpendicular to the plane and inwards. Okay, and there is a conductor PQRS, and the PQ arm is free to move. Okay, so we are moving this PQ arm towards the SR arm. Okay, length of this PQ is L, and this RQ is X at any instant. Okay, so figure 6.10, the arm PQ is moved to the left side. As we can see, PQ arm is moved to the left side, thus decreasing the area. So decreasing the area of this loop PQRS, this loop. And since we are moving this PQ towards left, we are decreasing the area of rectangular loop. This movement induces a current I as shown. Okay, so you can see the direction of arrows. So current will induce in this direction, in clockwise direction. Okay, so let the rod PQ is free to move and is being pulled to the left with a constant velocity V, as you can see in the diagram. Okay, let the length of the conductor PQ is L. It is also given in the diagram, and RQ is X. Thus area of the loop, then area of the loop will be at any instant when PQ is at then where Q point is at a distance of x from R. At that instant, area of the loop is A equal to PQ. This is a rectangular loop, so PQ into RQ, which is L into X. This is the area of the loop initially. Magnetic flux through the loop PQRS. So what is the magnetic flux? That is phi B equal to magnetic field into area. So BA cos theta. Cos theta, theta is the angle between the area vector and magnetic field. Okay, so loop is perpendicular, plane of loop is perpendicular to magnetic field. That is, area vector of this loop is parallel to this magnetic field. Okay, so theta will be 0 degree, so cos 0 degree 1. So therefore BA. Okay, and A we have area we have calculated. What is the area initially? LX. So BLX. As the rod PQ moves, the area enclosed by the loop PQRS changes. Okay, as we are moving this PQ arm towards this SR arm in the left direction, so area of this loop is decreasing. That means changing. Since area is changing, this flux will also change. Okay, therefore flux through the loop changes, and we know that according to the Faraday law of electromagnetic induction, EMF is induced when there is a change in magnetic flux with respect to time. Okay, so magnetic flux is changing. Okay, that's why EMF will be induced, and due to EMF induction, current will be induced in the loop. So according to Faraday's law, the induced EMF is epsilon equal to minus d phi b upon dt, which is equal to minus d by dt. And phi b we have calculated. What is phi b? BLX. Okay, and epsilon will be equal to minus BL. Magnetic field is constant here, so it will come out. Length, this L is also constant. It is not changing. Okay, so it is also constant. What is changing here? X, because we are moving this PQ arm towards this SR arm. So this X will change with respect to time. Okay, so what is this velocity? dx by dt, rate of change of this X. This is moving, this arm is moving towards the SR arm. PQ arm is moving towards the SR arm, and this is the initial distance X. Okay, so now we are moving towards the left, so this X is decreasing with respect to time. Okay, so due to this decrease of X, this dx by dt will be V. Okay, so this X is not constant, it is changing, so it will not come out of the derivative. Since velocity of the conductor PQ is along negative x-axis, that is V equal to minus dx by dt. Okay, so why minus sign is there? Because velocity is in, according to sign conventions, it is towards negative x-axis. Okay, also this x is decreasing, that's why negative sign is there. The change of x dx is negative. Okay, also according to sign conventions, direction of velocity is towards negative y-axis. That's why v equal to minus dx by dt. So minus dx by dt in this expression will become v. Okay, therefore motional EMF is given by epsilon equal to BLV. This is the formula for motional EMF. Okay, when a straight conductor is moved in a uniform constant magnetic field, marked as 6.5 equation. So magnitude of induced EMF epsilon will be BLV. Okay, does motional EMF formula directly results from applying Faraday's law to instances where B, V and L are all perpendicular to each other. Okay, in this case, velocity, magnetic field and the length L vector, or we can say length PQ, is along this. So this length is perpendicular to velocity and magnetic field is perpendicular to both velocity and this length. So Faraday law is directly applicable here to instances where B, V and L. This is a special case when all the three quantities B, V and L are perpendicular to each other. Then induced EMF will be equal to epsilon equal to BL V. Okay, in case of a stationary conductor, Lorentz force on its charges is given by F equal to QE plus V cross B equal to QE. Okay, now you may think what is the direction or polarity of EMF or direction of induced current. Okay, that thing you may know by this thing. Okay, or you can also apply Lenz's law here. Okay, it will oppose the cause which is producing it. Okay, so due to the motion of the conductor, EMF is inducing, so it will oppose the motion of the conductor. Okay, so in case of a stationary conductor, Lorentz force on its charges is given by F equal to Q E plus V cross B, that is equal to Q into E. Okay, because when conductor is stationary, velocity will be 0, so this V cross B will be 0. So force is due to Q into E. Okay, since V equal to 0, force on charge must arise from the electric field term E alone. Okay, but there is no electric field present in the space, only magnetic field is there. Then how Lorentz force is experienced by the charges? Okay, so Lorentz force is being experienced even if the conductor is stationary. Okay, since V equal to 0, force on charge must arise from the electric field E alone. Therefore, to explain the existence of induced EMF or induced current, okay, so EMF is inducing and current is also inducing. We are changing the magnetic field only. Okay, conductor is stationary. This is the another method. Okay, we have discussed that how EMF can be induced by changing magnetic flux, and how magnetic flux can be changed by changing the magnetic field, by changing the area, by changing the orientation of the loop with respect to magnetic field. Okay, these are the three methods to induce the EMF in a conductor or a loop. Okay, so to change the orientation, the application of change of orientation is used in the EMF induced due to the change of orientation of the loop is the principle of the AC generator. Okay, that we are going to discuss in the last of this chapter. Okay, but the change of area we have discussed in motional EMF due to the velocity of the conductor, area is changing, due to which magnetic flux is changing and EMF is induced. Now, if conductor is stationary, we are only changing the magnetic field with respect to time. Okay, conductor is stationary, so V cross V will be 0 and Lorentz force on the charges will be equal to F equal to QE. Charges present inside the conductor will be F equal to QE. Okay, mark it as 6.6 equation. Okay, so therefore to explain the existence of induced EMF, so EMF is induced, so we have to explain the existence. Then how EMF is inducing even if velocity of the conductor is 0. Okay, so magnetic force is 0, electric force is there, but there is no electric field. Then how forces on the charges is there? So to explain the existence of induced EMF or induced current, we must assume that a time varying magnetic field induces an electric field. Okay, so this is the explanation that how electric field is existing there. So time varying magnetic field induces an electric field. This induced electric field can cause charges to move, resulting in the induced current. It must be noted that electric fields produced by static electric charges have properties different from those produced by time varying magnetic field. Okay, so it is very important point, okay, that induced electric field is different from the electric field that we have discussed in electrostatic. Okay, that we have discussed in electric charges and fields. Okay, so it must be noted that electric field produced by static charges, this electric field is produced by time varying magnetic field, and the electric field produced by static charges that we have discussed in electric fields and electric charges and fields. Okay, so they both Both type of electric fields have different properties. Okay, the induced electric field form closed loops. Okay, we have discussed in the electric charges and fields that electric field doesn't form closed loops. Okay, that electric field is produced by static charges, but the induced electric field, that is time varying, that is induced due to time varying magnetic field, forms closed loops. That is the major difference between them. So they have different properties. Thus, a changing magnetic field with respect to time can exert a force on the stationary charges. Okay, so changing magnetic field with respect to time induces electric field and exert a force on the stationary charges. This is fundamental significance of Faraday's discovery that shows the relation between electricity and magnetism. Okay, so due to the change in the magnetic field, we are inducing the electric field, inducing the current, inducing the EMF. Okay, and in the moving charges and magnetism, due to the flow of current, due to the moving charges, we have seen that magnetic field is producing. Okay, so this is the fundamental significance of Faraday's discovery that shows the relationship between the electricity and magnetism. So time varying magnetic field is producing electric field. So this is relation between electricity and magnetism. In the previous section, expression for motional EMF is derived by using Faraday's law. The motion EMF expression can be derived from the Lorentz force, which is the force experienced by charged particle moving in a magnetic field. Okay, so motional EMF expression can be derived from the Lorentz force, which is the force experienced by the charged particle moving in a magnetic field also. Okay, we have derived the expression for motional EMF by using Faraday's law. Now we are going to derive the motional EMF expression by using the Lorentz force, that is force experienced by charged particles. Okay, so figure 6.10 again. Consider a rectangular conductor PQRS and conductor PQ of length L. The rod is moving with velocity V in a uniform magnetic field B, as we can see in the diagram. Magnetic field B is perpendicular to the velocity V here. Okay, it is clear. Now, free charge carriers are present in the conductor PQ. Since PQ is conductor, so free charge carriers are present. When conductor PQ moves with velocity V, free charges inside the conductor will also be moving with the same velocity. Okay, so PQ is moving with V velocity, so charges inside the PQ will also move with V velocity along with the conductor. Okay, thus Lorentz force F on a charge Q moving with velocity V in a magnetic field is given by. So what is the Lorentz force acting on the charges? Is given by F equal to V cross B, that is equal to QVB sine theta and n cap. This is the force with direction, where theta is the angle between V and B and n cap is the unit vector directed along the direction of force. Okay, so theta here will be, V and B are perpendicular to each other, so theta here will be 90 degree, so sine 90 degree will be 1. Okay, and if we are taking magnitude, then it will become QVB. Direction of the force is perpendicular to both velocity of the charge carriers and magnetic field, and it's towards Q. Okay, so direction of force will be, you can use right hand thumb rule to find the direction of the force here. So V cross B, so it is towards the Q. Okay, so direction of force is perpendicular to both velocity and charge carriers and magnetic field and is towards Q. Since the direction of V is perpendicular to B, thus theta is equal to 90 degree. Therefore, magnitude of force is given by F equal to QVB. This is the magnitude of force. Sine 90 degree 1 and direction we have discussed. Okay, so you can find the direction by using right hand thumb rule. Okay, or you can find the direction also by using right hand rule for vector products. Okay, so align your fingers in the direction of velocity and curl them towards magnetic field, and thumb will give the direction of the force. Okay, all charges experience the same force in magnitude and direction irrespective of their position in the rod PQ. Okay, any charge placed anywhere inside the PQ will experience the same force and in same direction. Okay, so now you can see we are not specifying the charge inside the PQ conductor. Okay, either it can be electrons, either it can be ions, positive or negative. Okay, that's why we are taking the default case as Q as positive. Okay, if we are considering that the charges that are present in PQ, and PQ is a metal and charges present in a PQ is electrons. Okay, then force on the electrons inside the PQ conductor will be in the direction towards P. Okay, if we are taking electrons, then the direction of force will be reversed. Okay, the direction of force according to right hand rule for vector products is defined or specified for the default case, that is for positive charges. That is, align your fingers in the direction of V velocity and curl them towards magnetic field, and thumb will give the direction. Okay, if the charges are negative, then this force direction will be exactly opposite to that. Okay, if electrons will be considered as charge carriers or free charges, then direction of force will be towards P. But here we are talking about generalized or default case where charges are free charges are taken as positive. So direction of force on the charges will be towards Q. So work done W in moving a charge Q from P to Q is given by W equal to QVB into L. Okay, so work done is equal to force into displacement. Okay, so force is towards Q. Okay, and from moving charge from P to Q, and length of PQ is L. So displacement is, total displacement is L. So work done will be force into displacement, that is QVB L. Since force and displacement in the same direction, so cos theta cos 0 degree will be 1. So directly F into displacement. Induced EMF epsilon is defined as the work done per unit charge. So epsilon will be equal to W upon Q. So substituting the expression for work done, we have epsilon equal to QVBL upon Q. So Q and Q will get cancelled out, and the same expression we got, epsilon equal to BLV of the motional EMF. So motional EMF expression can be derived using Lorentz force on the charge carriers present in the conductor. So this equation gives EMF induced across the rod PQ and is identical to equation 6.5. Okay, so example 6.6. A metallic rod of 1 meter length is rotated with a frequency of 50 revolutions per second. So what is this? Nu. Okay, 50 revolutions per second. Now, with one end hinged at the center and other end is at the circumference of the circular metallic ring of radius 1 meter about an axis passing through the center and perpendicular to the plane of the ring. A constant and uniform magnetic field of 1 Tesla parallel to the axis is present everywhere. Okay, so magnetic field is uniform across the region. Now, what is the EMF between the center and the metallic ring? Okay, so indirectly they are asking the EMF induced in the metallic rod between the center and the end. End is at circumference of the metallic ring. Okay, so metallic ring is having radius 1 meter. That means metallic rod of length 1 meter. That both things are indicating same thing. Frequency is given and magnetic field is given. Okay, so diagram you can see 6.611. So let's see the solution. So what are the given things? Length of the rod equal to radius of the ring, which is equal to 1 meter. Magnetic field is given 1 Tesla. Frequency nu is given 50 revolutions per second. Angular velocity omega is given, which is equal to 2 pi nu. So 2 pi into 50, that is 100 pi radian per second. We are not putting the value of pi we will put the value of pi in the final expression. When a rod rotates in a magnetic field, free electrons in the rod experiences Lorentz force. Direction of Lorentz force can be found using right hand rule for vector products. Okay, so when rod is rotating in the magnetic field, it is having some motion. Okay, due to its velocity, the free electrons present in the rod, so it is specified that it is metallic rod. So free charges here now are electrons. Okay, so electrons will experience Lorentz force due to the motion of the metallic rod, along with, so free electrons will also be in motion, so due to which they will experience Lorentz force. Direction of Lorentz force can be found using right hand rule for vector product, and electron move towards the outer end. Okay, now you can see how this rod is moving in the anti-clockwise direction. It is shown in the figure. Okay, so at any instant, direction of velocity will be tangential. Direction of linear velocity will be tangential to this point, and towards the, according to angular velocity, it is moving anti-clockwise, so it will be towards this, as shown by the arrow. Okay, so align your fingers in the direction of velocity, linear velocity of the rod at any instant which is tangent to the circle. Okay, and curl them towards the magnetic field. So thumb will point towards the center, but it is, the direction is defined for default case, positive charge. Here direction is, here free charges are electrons that are negatively charged. Okay, so thumb is pointing towards center, but in the case of electrons, when that are negative charges, so direction of force will be reversed. So direction of force will be towards Q, towards the end. So hence electrons move towards the outer end of the rod. Separation of charges generates an EMF. So separation of charges will be there. Electrons move towards the free end, that is towards Q. Okay, so electrons will move towards this. So towards center, there will be accumulation of, there will be positive charge. Okay, due to the movement of electron towards Q. So separation of charges generates an EMF across the ends of rods. Magnitude of the induced EMF, that is dE, across a small length dr of the rod. Okay, so we are taking, so this is motional EMF. There is a sub concept under the motional EMF, that is rotational EMF. Okay, if any conductor is not moving in not in the translational motion but in the rotational motion, so EMF induced will be motional EMF itself, but it is more specified term is rotational EMF. So we are here deriving the relation of EMF for the rotational EMF. Okay, so magnitude of induced EMF dE across a small length dr of the rod. So if we are taking any small element on this rod dr, okay, so magnitude of induced EMF will be dE equal to BV L. So L here is small element dr, so BV dr. So what is V? V equal to omega r. We know that linear velocity is equal to angular velocity into the radius r. This r is the position vector, sorry, from the center to that element. So if we are taking element at here, so from O to that element, distance is small r. So linear velocity will be omega r. Okay, so you can consider small element dr at a distance r from the center. So this is V equal to omega r, and dr is the small element, so we will put omega r. So dE, small EMF, magnitude of the induced EMF will be dE will be equal to B omega r dr. Okay, so total EMF across the rod from the center to the end. So from to center O to the end Q, the EMF induced in the whole rod from r equal to 0, distance from the center at center is 0. So distance from center at Q is r, capital R, that is radius. or we can say length of the rod. Okay, so from r to r equal to 0 to r equal to capital R. So we will integrate it. So total EMF induced will be epsilon equal to integration d epsilon will be equal to, what is d epsilon? B omega r dr, and integrating from 0 to capital R. So magnetic field is constant here. Omega angular velocity is constant everywhere on the rod. Only linear velocity varies. Okay, if any rod or body is moving, so angular velocity at any point in the body will be same. So omega is constant everywhere. So b omega will come out of integration, and inside the integration it will be r dr. So r dr integrating from 0 to capital R. So epsilon equal to b omega, and r integration of r dr will be r square upon 2. So r square upon 2 and limits from 0 to capital R will be equal to half b omega r square. Okay, so this is the expression for rotational EMF. If any rod of length, or we can say radius, or we can say length also, this r is can be replaced by the length also. Okay, here radius and length is same, that's why r is being used, but this r can be replaced by the length of the rod. This is length of the rod. Okay, so rotational EMF will be equal to half b, that is magnetic field, into rotational EMF, angular velocity, into the square of the length of that conductor. This is the expression for rotational EMF. Substitute the given. Now we will find out the EMF induced. So substitute the given values. What is given? Frequency is given. We have calculated the omega, that was 100 pi radian per second. B is given 1 Tesla and R is given 1 meter. So substitute the value to find the value of EMF. So epsilon equal to half into 1 into 100 pi into 1 square. So epsilon will be equal to 15 to 3.14. We are putting the value of pi, so it will be approximately equal to 157 volt. Okay, so EMF between the center and the ring. So between the center and the ring is 157 volt. Got it? Okay, next example, example 6.7. A wheel with 10 metallic spokes, each 0.5 meter long, is rotated with a speed of 120 revolutions per minute. What is given? Frequency. What is given? Length of the metal. This is spokes. Spokes means the wheel of a cycle. There are thin wires, or we can say rods, very thin rods, that are called spokes. Okay, so 10 metallic spokes in a wheel. Each spoke is of length 0.5 meter long. Okay, and speed, it is written speed, but it can be written other things also, but you have to identify this quantity by the unit. So it is written revolution per minute, that is, it is frequency. In a normal plane to the horizontal component of Earth's magnetic field HE at a place. So horizontal component of Earth magnetic field is present here, so which is given by 0.4 Gauss. 1 Gauss is 10 raised by minus 4 Tesla. Okay, it is also given in the question. So what is the induced EMF between the axial and the rim of the wheel? Rim is outer circular path, circumference of the wheel. So what is the EMF induced between the axial? Axial is the center of the wheel. So between the center and circumference. This problem is similar to previous problem. Okay, but now there are 10 metallic spokes. But you can see all the metallic spokes, one end of the metallic spokes are connected to center at the axial. Okay, and other end of all the spokes are connected to the rim of the wheel. Okay, so they are connected in parallel. Their ends are connected to a common point. So they are connected in parallel. So EMF induced along all the spokes will be same. So we can find the EMF induced across one spoke. So it will be EMF induced across all the spokes. Okay, so the net EMF induced across the axial and rim of the wheel will be same. That is EMF induced in all the wheels, all the spokes. So that will be same and all are in parallel. So EMF across all the EMF is also potential difference, also a voltage, type of voltage. Okay, so EMF induced across all the spokes is same. So EMF induced between the axial and the wheel will be same as EMF across one spoke. Got it? So let's see the solution. So we will use the formula that we have derived in the previous example. Okay, so length of the spokes is given L equal to 0.5 meter. Frequency nu is given 120 revolutions per minute, which is equal to 120 upon 60 revolution per second. Okay, we have to convert frequency into SI units. Okay, so revolution per minute, we have to convert minute into seconds. So 120 upon 60 revolutions per second, which is equal to 2 hertz. Magnetic field B equal to HE, which is equal to 0.4 Gauss, which is equal to 0.4 into 10 to the power minus 4 Tesla. Okay, so induced EMF between the axial and the rim of the wheel. So epsilon equal to half B L square omega. We have derived in example 6.6 half B omega R square. So I have explained there that radius, in that equation, radius of this circular ring and the length of the rod was same. That's why we are using these terms interchangeably, radius and length. Okay, but in actual expression, that R is representing the length of the metallic rod. Okay, so here L is the length of the spoke. So EMF induced will be equal to half BL square omega, derived in example 6.6. Where B is magnetic field, L is the length of the spokes, and omega is the angular velocity of the wheel. So angular velocity of the wheel we will calculate. We know the frequency. So omega is equal to 2 pi nu, 2 pi into 2, which is equal to 4 pi radian per second. So substituting omega equal to 4 pi, then induced EMF will be equal to half BL square omega half into BL square into 4 pi, which is equal to 2 pi BL square. Okay, now substituting the value of B and L also. So B is here 0.4 into 10 to the power minus 4 and L is 0.5 meter. So epsilon will be equal to 2 into 3.14 into 0.4 into 10 to the power minus 4 into 0.5 into 0.5. So epsilon will be equal to 3.14 into 10 to the power minus 4 into 0.2. So finally it will be equal to 6.28 into 10 to the power minus 5 volt. So this is the EMF induced across one spoke. Okay, since spokes are, this is the EMF induced across one spoke and each spoke is identical. So EMF induced in each spoke is the 6.28 into 10 to the power minus 5 volt. Since all the spokes are connected in parallel, so the EMF across axial and wheel will be same. Since all the spokes are in parallel, so EMF between the axial and the wheel will be, rim of the wheel will be same. Okay, we know that if any components are n number of components are connected in parallel, so potential difference across all the components remains same. Similarly, if EMF induced across one spoke is this and every spoke has EMF, same EMF across them, so since they are connected in parallel between the rim of the wheel and axial, so the EMF induced between the axial and the wheel will be same. Therefore, induced EMF between the axial and the rim of the wheel is 6.28 into 10 to the power minus 5 volt. Okay, so let's have a quick recap. So motional EMF is the voltage induced when a current moves through a magnetic field caused by separation of charges due to magnetic force on the electrons. The formula for motional EMF is epsilon equal to BLV. Okay, where B is the magnetic field strength, L is the length of the conductor, and V is velocity perpendicular to the magnetic field. Direction of induced EMF follows the right hand rule, aligns your fingers in the direction of motion and curl them in the direction of magnetic field, the thumb indicates the direction of force on the charges. Okay. In closed circuits, motional EMF generates a current. Okay. Current is induced when EMF is induced if circuit is closed, which creates a magnetic force opposing the motion. That is according to Lenz's law. Okay. Direction of induced EMF you can find using right hand rule. You can find the direction of force on the charges. We have derived the motional EMF by using Lorentz force also. So you can do like that. Common applications include electrical generators, where mechanical energy is converted to electrical energy through motion of the conductors in magnetic field. Also, when we rotate the coil in the magnetic field, okay, there is a motion of the coil also along with the change in orientation. Okay, so common application is electrical generators. What is the motional EMF? Some practice question you have to do yourself. What is the motional EMF? Explain how it is generated when a conductor moves in a magnetic field. Why does the direction of induced EMF reverse when the direction of motion of the conductor is reversed in a magnetic field? Explain why no EMF is induced when a conductor moves parallel to the magnetic field lines. A metallic rod of length 20 centimeter moves with a velocity 5 meter per second. V is given, L is given. Perpendicular to uniform magnetic field of 0.4 Tesla. B is also given. Calculate the induced EMF uh, between the ends of the rods. You can calculate. A conductor of length 15 centimeter moves with the velocity 2 meter per second at an angle 30 degree to a uniform magnetic field 0.5 Tesla. Find the induced EMF across its ends. Okay. Now it is moving at an angle theta, not 90 degree. Okay. So you have to think about that also. So thank you, but don't go anywhere. We have to do DPP also. Okay. First question. A metallic rod of length 1 meter is rotated with a frequency of 50 revolutions per second in a plane perpendicular to uniform magnetic field of 1 Tesla. The axis of rotation is at one end of the rod. And what is the induced EMF between the ends of the rod? Okay. So you have to solve it and write your answers in the comment section. Okay, third option. ठीक है. A wheel with 10 metallic spokes of 0.5 meter each rotates at 120 revolutions per minute in Earth's magnetic field 0.4 goes. The induced EMF between the axle and rim is. Okay, this is the same question. Okay, first option. A straight conductor PQ of length L moves perpendicular to magnetic field with velocity V. The motional EMF induced across PQ is. Yes, first option. In a stationary conductor placed in a time-varying magnetic field, the induced EMF is due to Lorentz force from magnetic field, electric field produced by time-varying magnetic field, motion of free charges, or static electric charges. Yes, B. A rectangular loop with movable arm PQ length L is pulled left with velocity speed V in uniform magnetic field perpendicular to the loop. The induced EMF is. BV upon L, BLV, B square L. Yes, second. Okay. Well done. All the options are correct. Okay. I hope you enjoyed the session. Thank you.